Your users table has 1,000,000 rows. One query, filtering by email, takes 4 seconds. Why so slow? With no index, the database has exactly one option. Check every row, one at a time, from the very first to the very last. On 100 rows, that's instant. On 1,000,000 rows, checking every single one takes real, measurable time. And it gets worse under load. 10 users running that same query means 10 separate million-row crawls all at once. An index is a separate, pre-sorted structure built just for one column, so the database never has to crawl the whole table again. With that index in place, the exact same query returns in milliseconds. Same data, same hardware, completely different cost. One line of SQL creates it, but what that index actually is and how it finds a row that fast is the real story of this course. Over the next chapters, we will build that structure from scratch, the B tree, and exactly why it makes this jump possible. Most people picture a tree as tall and narrow. A database index is built the exact opposite way. Why? A B tree node doesn't hold just one key. It holds many sorted keys at once, often hundreds, packed into one block. Between each pair of keys sits a pointer to a child node, covering everything in that range. More keys per node means more children per node. Because each node fans out to so many children, the whole tree stays shallow, even with millions of rows underneath it. Search just compares your value against the sorted keys in a node, picks the one gap it falls into, and drops down one level. With enough keys per node, 3 or 4 hops is enough to reach any one of 1,000,000 rows. That's the shallow part paying off. A narrow 1 key per node tree would need 20 hops for the same 1,000,000 rows. Wide and shallow beats tall and narrow badly. That's the whole shape of a B tree pack. Many keys per node. Stay wide, stay shallow, and every search stays just a few hops long. A leaf node is completely full. A new row still has to go in there. What actually happens? Every node has a maximum capacity. Once it's full, there is no more room to simply insert one more key. So the node splits. It divides its keys roughly in half, creating 2 new nodes where there used to be one. The middle key gets pushed up into the parent, along with a pointer to the new second node. The parent just gained one more entry. If that push-up overflows the parent too, the parent splits the exact same way. Splits can ripple all the way up the tree. If even the root splits, a new root is created above everything, and the whole tree grows exactly one level taller. Rare, but that's how it happens. Deletes work in reverse. A node that gets too empty either borrows a key from a full neighbor or merges with it if the neighbor is sparse too. This self-balancing is automatic and constant. Every insert and delete quietly keeps the tree wide, shallow, and sorted. You indexed country. Your query filters by country and city. Why is it still scanning? A single column index on country groups matching rows together, but within each country group, city is still totally unsorted. A composite index on country, then city sorts by country first, and sorts by city inside each country. Like a phone book, last name, then first name. Now query for France and Paris dives to the France group, then straight to the Paris rows inside it. One clean path, no scanning. But a query for just city, skipping country entirely, gets almost no benefit. City values are scattered across every single group. Flip the column order, and the trade-off flips too. This is why the leftmost column of a composite index matters so much. You can stack more columns, country, then city, then sign-up date. Each one only helps. Once every column to its left is also filtered on. So design composite indexes around your actual queries. Put the column you always filter on first, and build inward from there. The index already found your row. Why does the database go dig through the table again? A normal index only stores the column it's sorted by, plus a pointer back to the full row on disk. So if your query also wants the email or the sign-up date, the database makes a second trip into the table just to get it. That second hop happens for every single matching row. On a big result set, those extra disk trips add up fast. A covering index fixes this by stuffing the extra column straight into the index right next to the key. Now the query is fully answered by the index alone. It never has to touch the table's heap storage at all. This is called an index-only scan, and it can be several times faster because it skips the entire second trip. The cost: a fatter index takes more disk space and slightly slower writes. Cover only the columns you actually query. Two kinds of index, both promise instant lookups. So why does almost every database default to the one that looks slower? A hash index runs your key through a hash function and drops it into a bucket. Exact match, instantly, no comparisons needed. But ask for everything between 10 and 50, and the hash index is helpless. Hashing deliberately destroys any sense of order. A B tree keeps keys sorted, low to high, across its leaves. Order is the entire point of how it's built. That same range query just walks to the starting point, then reads forward until it passes the end of the range. Simple. For a pure exact match, hash can edge out slightly ahead. For anything involving order or ranges, the B tree wins completely. You cannot fix this by tweaking a hash index. Scattering keys for speed and keeping them ordered are opposite design goals. That's why almost every database defaults to the B tree. It handles both exact matches and ranges for a small extra cost. Even with a perfect index, one thing can still make your query slow, where the data physically lives. Reading from disk, even a fast SSD, is dramatically slower than reading from memory. That gap is the real bottleneck underneath everything. So databases keep a buffer pool, a big chunk of RAM that holds pages recently read from disk, the way a browser caches images. Ask for that same page again, and the database serves it straight from memory. Disk is never touched a second time. For frequently accessed data, this buffer pool hit rate climbs extremely high. Most real-world queries barely touch the disk at all. When the pool fills up, the database evicts the least recently used page to make room, betting that recently used data stays useful. A page nobody has touched in a while is not cached. That first request pays the full disk cost, then it too gets cached for next time. An index tells you which page to read. The buffer pool decides whether reading it costs a disk trip at all. Speed is both working together. You have an index. The database sometimes ignores it anyway, on purpose. Who's making that call? Every query first passes through a query planner, which estimates the cost of several different ways to run it. One option is a sequential scan. Just read the whole table. Straight through, simple, and surprisingly fast for reading things in order. Another option is an index scan. Jump through the sorted index and follow pointers to just the matching rows. When a query returns a tiny slice of the table, the index scan easily wins few rows, a few precise jumps. But a query returning most of the table forces the index path into scattered random jumps all over the disk. The straight sequential read wins instead. A third option: the bitmap scan gathers matching row locations first, sorts them by disk position, then reads them back in order, a middle ground. Running explain in front of any query shows you exactly which plan it picked and why the planner thought it was cheapest. An index is not a command, it's an option the planner is free to skip, whenever skipping it is actually faster. More indexes should mean more speed. This table has 10 of them, and writes have gotten painfully slow. Why? Every index is a separate structure that has to stay in sync. One insert into the table means one insert into every index too. 10 indexes means up to 10 B-tree updates per write, each one a possible node split rippling through its own tree. This is called write amplification. The more indexes you add, the heavier every single insert, update, and delete becomes. An unused index still pays this tax on every write while giving you nothing back. It's pure cost with zero benefit. Indexing a column with very few distinct values, like a true or false flag, barely narrows the search at all. Barely worth the cost. Heavy deletes leave dead entries behind inside the index too, called bloat, until routine maintenance reclaims that wasted space. So indexing isn't free. Index the columns your real queries actually filter on, and resist indexing everything just in case. 9 chapters, 1 simple table? Let's put the whole speed story back together in 60 seconds. It starts with the index, a wide, shallow B-tree that turns a million-row crawl into 3 or 4 quick hops. That tree self-balances on every insert and delete, can stack multiple columns in order, and can even carry extra columns to skip the table entirely. Hash indexes are faster for pure exact matches, but only the sorted B-tree handles ranges at all. Beyond indexing, the buffer pool keeps hot pages in memory, and the query planner freely chooses whichever path is actually cheapest. And every index has a cost. Slower writes, wasted space if unused. The goal was never index everything. It was index deliberately. Indexing, caching, and planning working together. That is the entire mechanism behind why a fast database feels instant. Like and subscribe for more.